Thank you. So, on behalf of all of the 8 partners of the MySOIL project, I wish to welcome you all. I'm Valentina Vernizzi to this open day, and it'll be a moment to share in the advancements of this project, and I hope it'll be an interesting moment for everyone here. We have a very rich program, so I will ask speakers to stick to the program and their allotted time. In the afternoon, there will be a visit who has adhered to it. Later on, we will provide a few indications of how the afternoon will be organized and how we will get onto the bus and everything. So again, I wish you all a very fruitful day, and I will hand over the floor now to Guido Bonfedi, Head of Environmental Engineering and Market Development of Eni Rewind.
Thank you, Valentina. Good morning, everyone. It's a big pleasure to see all of you here and all the colleagues that are linked via streaming. I hope this could be a very fruitful morning and a very fruitful day. And as Eni Rewind, I'm very glad to be here with you today. I think it's a very important opportunity to share the advancement of our project. And so I don't want to steal time to the other presentation. And so only to thank our Italian partner, the University of TUSCIA, with Professor Petruccioli and Professor D'Annibale, and our team coordinator, Eurecat, that is with us today. So just to remain in the time, I only want to leave the stage to Professor Petruccioli, just to introduce it to the other argument. So have a fruitful morning and a fruitful day. Good work.
Thank you. If I can have the presentation, just a few minutes for presenting the University of TUSCIA and the department and the research group. Anyway, I am starting now. Oh, okay. So, I shortly present the University of TUSCIA in Viterbo and the research group involved in MySOIL project. University of TUSCIA is in Viterbo, a middle-sized city in Lazio region, in north of Rome. Viterbo, although is a middle-sized city, is considered the largest medieval center in Europe. Anyway, is famous for this aspect. Is approximately 80 kilometers in north of Rome, and from the 1979 Viterbo has a public medium-sized university, University of TUSCIA. Here you can see some data related to the university. Not so high number of students, but very motivated. Good staff, 6 departments, and very good research area in terms of research activity, several national, international, European projects, spin-offs, and so on. As I said, the university is divided in 6 departments, 3 of which are the scientific department, and I represent here the Department of Innovation in Biological, Food, Agro-Food and Forest Systems. I am the director, unfortunately, of the department. As you can imagine from the name, this department is a multidisciplinary one, in which are merged biological, biotechnological, chemical, food technology, forestry expertise. As for the research group involved directly in MySOIL project, it is constituted by microbiologists, biochemists that have accumulated expertise in applied microbiology and particularly in applied mycology. This expertise was focused directly on the bioremediation processes, specifically addressed to soil contaminated by persistent organic pollutants. Here you can see several expertise and methodological approaches that we can provided. Of course, characterization of contaminated soil under different point of view, ability to isolate and characterize microorganisms, able to actively decontaminate, actively able to decontaminate organic pollutants, ability to use allochthonous indigenous microorganisms in bioaugmentation processes, and so on. Here I wanted to list some case studies, and so contaminated sites in Italy and Europe on which we was involved in the study of technical possibility to apply bioremediation processes. And finally, here you can see the list of the participants to the project: myself, Professoressa Silvia Crognale, Alessandro D'Annibale, agricultural biochemist, that is the scientific responsible of the project, and the PhD student, David Lelli. Thank you for the attention. So, okay.
I can introduce myself, but thank you. Hello, everyone. My name is Jofre Herrero. I'm the coordinator of MySOIL project. If the presentation just appears, it will be great. I'm representing Eurecat Technological Center from Catalonia. Okay, perfect. So I have the job to introduce you to the MySOIL project without telling you a lot about it, because later on this morning you will know more about it. And then at the end of the presentation, I will also introduce Eurecat Technological Center. So MySOIL, a step further in bioremediation, mycoremediation for soil recovery. So we are working mainly, I know, in Europe. In Europe we have around 2.5 million polluted sites. From them, we have around 14% that need remediation. And from these 340 sites, we have around 35% that are polluted by petroleum hydrocarbons, taking into account also the polyaromatic hydrocarbons. And we also know that depending on the structure of the pHs, the petroleum hydrocarbons, aliphatics are more easy to biodegrade, aromatics a little bit harder, but then asphaltens and resins are the more unlikely to be biodegraded. Going further, currently we have several remediation strategies. The first one, per se, it's not a remediation strategy, it's just landfilling, excavating the soil and putting somewhere else. But a lot of countries are doing that in Europe. A second remediation strategy is the physicochemical remediation, which is very efficient to all types of hydrocarbons, but have a high, it's expensive, plus they need a lot of energy. And then we have the conventional bioremediation, what we call it the bacterial biopile, which is cheaper and consumes less energy, but doesn't arrive to the same efficiency or removal efficiency with the long chain TPHs. And what we're trying to demonstrate in the MySOIL project is that mycoremediation, the use of fungi inocula plus organic substrate, could reach similar removal efficiencies while keeping the low energy consumption and the lower price as the conventional bioremediation. So after this small introduction, we are going already to the main objective of the project, which is demonstrating mycoremediation, which is already demonstrated at lab scale, but we want to arrive to the pilot. So We want to demonstrate it not only that works, but that it's suitable, cost-effective, and sustainable. So we are working in this, this scheme where we start with the site characterization, moving to the biotratability test, small pilots, and finally to the pilot mycopiles. That we are moving from 1 liter experiment to 1 cubic meter till 50 cubic meter. This last step is the one that we are going to visit this afternoon. And also, you will see in this map where we have our pilot sites that are mainly in Italy. We have one site in Borgo Fatti, and the one that we are going to visit is, I will pronounce badly, I'm sorry, Cislano, but of course it's not well pronounced. Then we have another one in France, in Rouen, also bad pronounced. And in Spain, we have 2 more, that these ones I will pronounce correctly, that are Huelva and Burgos. Going further, yes, with the, I won't get inside any results because my colleagues are going to present it. But what we want to assess, it's in the pilot scale. These are some pictures of raw pilots, how they build their mycopiles. We want to assess not only the TPH or petroleum hydrocarbon removal tags, but also we want to assess it, or we want to use some advanced monitoring tools. Mycotraps that are in situ microcosms that our colleagues from ISODETECT are going to talk about it, and also the phospholipid fatty acids analysis and some isotope compounds analysis. But we also want to say something about the soil health indicators that, as some of you already know, the European Union are working in the soil monitoring law. And topics like soil functionality, reduction of ecotoxicity, microbial abundance and structure are really interesting. So we don't want only the TPH removal, we also want that the soil that we are going to remediate is in a better conditions than before. And then other parameters like the human health risk assessment, life cycle assessment, life cycle cost, and socioeconomic impact. Going a little bit through the project, we have other outputs. One of the main outputs will be the creation of guidelines for implementation of mycoremediation. But as you already see, we only have 5 pilot sites. So we are working with Novobiome and Eurecat to doing more replicability experiments. Small experiments, microcosmos, in order to assess the different conditions of different soils. Also, we will work in the transferability. Transferability means working mycoremediation in other pollutants, and we are going to work with the heat thermal fluids. This part of the task will be held by Universidad Autónoma de Madrid and Kepler, the Spanish colleagues. Then we are going to move to the contribution to the EU standards and regulation, namely white paper, where we're going to assess the legal and administrative barriers that we can find in order to implement mycoremediation in an efficient way. And also, by the end of the project, we want to generate a template for describing the best available technique or emerging technique for the mycoremediation in order to increase this, that the mycoremediation is more used in other contexts. And finally, you can check that we are doing some dissemination activities, not only the online presence that we have in LinkedIn on our webpage, but also we are participating in conferences, congresses, workshops. This open day, that is the second that we are holding by the consortium. Plus, we are also producing some articles that recently we just got almost approved, a second manuscript that we were working on it. So, this is the consortium. Eurecat, as I already introduced, Università della TUSCIA and ENI, the Italian colleagues that already introduced themselves, But then we have two more pairs of partners, the ones in Spain, Universitat Autónoma de Madrid and Kepler. The colleagues that are working in France, that is the Valgo plus Novobiome. Novobiome is from Belgium, but they are working in the same pilot site. And Isodetect from Germany. You will hear more about later. So I would like to introduce some few slides about Eurecat. Eurecat is a technological center of Catalonia, where we are working in a lot of different topics, but to say some ones are circular economy, decarbonization, wastewater management, air pollution reduction, among others. But basically what we do is try to fill the bridge between the basic science from the universities and other research centers to the companies and business. So that's why I'm here, and Eurecat is in this MySOIL project. Going further, Eurecat have different areas: industry, digital, biotechnology, and sustainability. Mainly, I come from the soil line. And in this line, we are mainly focused not only in the soil sediment remediation strategies, but we are also working in groundwater, in quality monitoring and risk assessment, and we are also working in governance and social engagement, plus the modelization of remediation and the water within the sediment. Finally, here is the team. I'm just me today here in this open day, but you can see that we have an interdisciplinary team in the that is backing me. Thank you all. And I think we are moving to the second block, if I'm not mistaken. We are doing a small change of names.
Thank you very much. So thank you very much, everybody. So I just introduced myself. I'm Andrea Franzetti from the University of Milano Bicocca, and I have the pleasure to have Silvia Crognale from the University of TUSCIA co-chairing with me with this interesting session. So in this session we have 4 speakers, and the first one is Federico Silvestri from ISPRA. And the title of his presentation is Emerging Technology and Diffusion and Acceptability. And so I give you the floor, please.
Hello, everyone. I'm Federico Silvestri from ISPRA. I'm a biologist, and I work in 2 departments, biology and geology department, dealing with remediation techniques for contaminated states, and agroecology and forestry, and so more things. So I will present you something about emerging technologies, diffusion and acceptability. Then this is ISPRA. It was built in 15th June of 2016. It was called APAT and AMPA before. It's the Environmental Research and Protection Institute, Superior Environmental Research and Protection Institute, dealing with environmental control and monitoring and technical scientific support to the Ministry of the Environment. In our institute, we do also research, control, assessment of everything. So we deal with everything about environment. SNPA is the System National of Protection Agency, and dealing with 41 national interest sites for contaminated sites, remediation, risk assessment, characterization, risk assessment, and remediation. We also write publications such as guidelines and reports, participate in meetings and technical tables, everything about environment issues and problems. So we also participate in the international context in live projects, the Impel network. I'm dealing with Impel network in particular in phytoremediation and in Soil Hub. Something about Horizon Europe projects, the UNEP, that is the United Nations Environmental Assembly, in which I deal with nitrogen questions, nitrogen cycle questions, issues. So what is produced in the context of contaminated sites? We support the Environmental Ministry of National Interest sites, and also environmental regional agencies and regions to design and test in characterization and remediation techniques and procedures. We manage the MySOIL database, that is an innovative database dealing with everything about the state of contaminated sites in Italy. And we prepare protocols, reports, and guidelines. This is the states of contaminated soil remediation techniques in Italy. We have the 32% is still used to excavate and dispose in landfill, and this is not a good thing. We have 22% of containment procedures, so only to limit the extent of contamination. And about the biological techniques used, we have only 14%, and principally used for bioremediation, land farming, and phytoremediation. So in this case, these days is dedicated to mycoremediation. That is a very innovative tool. In fact, I appreciate this because there is finally an in-field application of mycoremediation. Because as I research on the network, I only found some laboratory or mesocom scales examples. So the use of fungi in field treatment is very innovative, and we hope it will be good, and there will be a good efficiency, because we have, as I will show later, a lot of examples of use of plants and a few examples of use of fungi. But fungi and plants can work also together, as we can see. So the MySOIL project that has been before introduced is in a good occasion for this in this sense. So I want to show you something about the normative innovation for soil. Soil is an important environmental matrix that has not been yet very studied, yes, but we have not direct for soil. But we will arrive on this, because the European Green Deal of 2019 is a package of policy initiatives which aims to set the Europe with for a green transition with the ultimate goal of reaching neutrality climate by 2015. So we have a zero pollution ambition for a toxic-free environment, and the EU soil strategy combines with EU biodiversity strategy in preserving and restoring ecosystems and biodiversities. So this package includes initiatives including also environmental protection. This is the good path to have soil in the center of interest for environment, because we have interest principally in air and water before. So for anti-soils, to reach healthy soils, we have introduced to a new soil monitoring law that has been proposed to increase the value of soil and its resources. We have something on July of this year, an introduction to a new soil monitoring law that points in which soil is in the center of interest. So we have the objective is very ambitious to reach healthy soils by 2050, and we have is the soil monitoring law provides monitoring and assessment, sustainable soil management, so to deal with contaminated sites, and then a reporting to inform public and evaluation. This is the problem is that in Europe, we have 60 to 70% of soils that are currently unhealthy, and we have to solve this problem. So as nature-based techniques, as I was telling before, phytoremediation is one of the most known and used. Is provided in Grill D for use soil strategy for 2013. Is one of the most sustainable options to decontaminate soils. It's the more sustainable and one of the most widely used. You know what is phytoremediation, but he has some paths. And one thing to say, that plants that do not work alone to remediate soil, but need fungi and bacteria, but in particular fungi. And in this context, it's important to link fungi to plants. Favorite areas for phytoremediation are inherited environmental liabilities like orphan sites. We use phytoremediation where there is little interest in the area, sites with the disproportion with intervention costs and the commercial value, widespread contamination in rural areas, and when we have naturalistic and landscape values to promote naturalistic and landscape values. We have two examples of national interest sites with phytoremediation activities since some years. It's Bagnoli Coroglio in Campania, and I will show you that if we use plants in combination with mycorrhizal fungi to solve organics and heavy metal contamination, or also here in Lombardy, Brescia Caffaro, is used contamination phytoremediation for contaminants as PCB, PCDD, arsenic, and mercury. In particular, the rise of degradation for PCB and PCDD. And this is very interesting because roots of plants act together with fungi in with mycorrhiza, and this is the case of rise of degradation for organics like the MySOIL project. So going all this, I start the last. We point attention of new. Emerging remediation technology as phytomining. Phytomining is mining and recovery of critical raw materials, one of the most important issue of these years. And phytomining is an environmental friendly techniques for extracting metals from ores and contaminated sites. These techniques that use plants to absorb in the aerial parts these critical raw materials that I will show you just now, has emerged as an ecological techniques to extract where traditional mining is not competitive. If you don't know what they are, critical raw materials are raw materials of high economic importance in Europe with high risk of supply due to their concentration, source, and lack of good. And we have affordable substitutes. So there is a European project in which I'm involved, that is the CIRAN. It is a plan for sustainable resource extraction towards the responsible sourcing of critical raw materials in protected zones. This is important. And this project promotes the use of nature-based solutions to recover this critical raw material inside Natura 2000 seeds, parks, and something like that. Because we have a need of these materials, and we have the problem to extract these also in natural areas. And we prefer to use natural ways to extract. So how we extract these critical raw materials? By hyperaccumulators plants that are commonly used, and they take metals from soils and translocate to the roots and aerial parts. Then, after the hyperaccumulation, the aerial parts are harvested and disposed to recovery. And there are some extraction techniques that recover these materials from shoots, roots, leaves, and so on. These are examples of some vegetables used commonly to recover critical raw materials, and there is the efficiency of recovery indicated. The icory, there's a Eucalyptus, like noci, and some fern, Dicranopteris linearis, that recover a lot of critical raw materials for contaminated mine area. This is a good example of Phytolacta americana and Pronephirium simplex that have also good results. Why phytomining is a good emerging technologies remediation? Because have an economic viability and potential for diffusion. Their strength is the biomass production, the recovery of CRMLs in soil and plant matter, and the effectiveness of enrichment extraction process. The United States Department of Energy suggested that the extraction of material containing at least 300 milligram on kilogram of critical raw materials may be profitable for recovery. So the research on this science is going on. Another emerging remediation technology is the one to disrupt the natural origin abscesses. This is a very innovative technology because we have a problem, as you know, of abscessus fibers widespread everywhere. And some studies have enlightened that some bacteria, lichens, and also fungi, as I show you in the next slide, and the production of natural acid from plants are able to remove large quantities of heavy elements, reducing the danger of these fibers. How do they act? They act removing iron and disrupting as abscessor fiber, and we arrive to have some abscessus fiber not toxic due to the metabolic activities of bacteria, fungi, and lichens. So this is the virtuous cycle. The iron supports plants' growth. Plants provide carbon source for microbial community, and microbial interaction remove ions and reduce toxicity. Of course, these studies are at laboratory scales. We have not some in-field application, but as your study for mycoremediation, also this aspect of removal of natural abscessus fiber should be considered in the future. So I show you that fungi are potential agents of bioremediation, and how they work. Fungal hyphae can form a web of thin strands that bind abscessus fibers, making them less liable to escape in the air. So we use the natural capacity of fungi of making these strands, and to capture asbestos fiber. So for the professor of TUSCIA, I show you some examples of fungi that are used: Fusarium oxysporum, Mortariella hyalina, and Odiodendron maius as fungi used for this objective. So I conclude tell you a question: is emerging technologies have a societal acceptability? And I think yes, because nature-based technologies are considered environmental beneficial, cost and effective, with high societal acceptable, and in alternative to conventional physical and chemical remediation processes. And this was told in 25 and 5 by Pilon and Smith. The trends for acceptabilities are the importance, in this case, of use of plants, but also use of fungi is similar, of cost effectiveness, no risk for environmental and health, increasing in green areas and reforestation if we use plants in combination with fungi, and maintenance of soil structure, increase on biodiversity, because these studies, as MySOIL, the advantage of increased biodiversity and improvement of landscape perception by people. And final, but is not the least, the contrast of climate change. So this is what these are the conclusion of my intervention. Thank you for the attention.
Thank you. So thank you very much, Federico, for your very complete overview of nature-based solution applied to soil health. I asked the organizer, but I guess that the discussion will be at the end of the morning session, so keep your question for that time. And so it's a pleasure to introduce the second speaker of this session. So the talk is entitled "The Pros and Cons of Conventional Treatment for TPH Removal," and will be given by Laurent Tannenberg from Valgo Group in France. The floor is yours.
Thank you. So I'm representing a remediation works company. I'm a research director in this company, and my job is to transform the academic knowledge into applicable know-how. We need to ask questions to the scientists. How could we manage with this? And that's why I'm participating to this transfer project. It could be useful for the future for us. And I will show you how we are going for this. I will repeat a bit what Jofre has spoken about. If we check this diagram of the frequency of type of pollutant, if you add to classical pH or classical petroleum hydrocarbons, PAH, BTEX, petroleum compounds represent more than 50% of the number of pollutants we are encountering on the site. So because everybody uses hydrocarbons, even if you have not an industry for hydrocarbons, every type of industry, also private persons, have there for the heating, for their car, so there is production plant, storage, distribution, until the tank you have in your home or in your car. So this everywhere is ubiquitous, and we are facing very often to these issues with this pollutant. Because it's very common pollution, we developed a lot of techniques depending, I will classify them by the technique physical, chemical, and biological, and also depending on the matrix where you will find those pollutants in gases, in liquid pure phases, dissolved in the groundwater, or maybe adsorbed to the solid matrix. For example, as soil gases, you may physically remove them by soil vapor extraction. It's one of the name of the venting technique. Chemically, you may have catalytic oxidation. You pump and then you transform them on a platinum foam, for example. There are different type of techniques. If you have liquid pure phase, the best way first to remove it is to pump and separate the phase and to pump only the oil or the gasoline you have in the soil. If the components, for example, BTEX or low short chain TPH, you may sparge because they're dissolved in the phase. You're putting bubbles in the water to remove them from the water, and also diffuse some strong oxidant to make a chemical oxidation in situ. Or you may, by the same type of bubbling, you may create a biosparging that stimulate the endogenic bacteria or microorganism, and so stimulate the natural biodegradation. Sometimes it's very suitable. We will then focus about the absorb phase because fungal remediation will target this part of the TPH pollutant. I will put away around 50% of dig and dump technologies. That's just make a hole and put this to the landfill. That's not the scope of the presentation today. As physical technique could be applied in situ or on site. We may have thermal desorption. This is one of modern recent technique achieved on the field in the last 10 years, not before. It's a very strong possibility. Other physical possibility is to make a soil washing. You just flush the soil and separate the coarse grain, sand, and gravels from the fine and clay fraction containing the hydrocarbons and also sometimes the metals. So it's a very efficient way to do this. Chemically, if you want to add some oxidant, you have to produce a soil mixing is much harder than just injection. You need special device to mix with the soil. And biotreatment could be bioventing, ventilation into the soil to stimulate the microorganism in place, or just build a biopile, a type of solid bioreactor. And I will focus a bit of this line just to show you what it is, how it's going. If you want to apply a venting, bioventing, it's simple to install a pump and then a wells or screen wells to create an air stream. Fresh air is coming with oxygen. Oxygen is stimulating the biological life, and you could enhance the biodegradation. In the same time, if you have volatile compounds, they will go through this flow of air and could be extracted. So you need filters or vapor treatment unit after your extraction. So on the field, you will see some manifold like this because you need several wells depending on the physical properties of the soil. You have to create a network of several wells, venting wells. It's a very simple technique. You may run it for months. It's used for maybe 20 or 30 years, so it's considered to be a very mature technique. Whatever you do, if you apply biology or just physical properties, you remove the existing vapors, some toxic vapors that could accumulate before you start the work. But it's only applicable for enough volatile compounds. Depending of the pressure, partial pressure, vapor pressure, some compounds are not feasible by this technique. It could last very long. Sometimes we put a machine during months during the building of the next factory or next houses. It could be longer than the time of the real work of building. And physical properties of the soil strongly influence your results. If you have a too clayey soil, you will never have a suction effect big enough to produce a fast removal of the pollutant. And also, could have interaction, for example, for a very organic soil, interaction between the organic matrix and the pollutant, and whatever the type of blowing you may produce, you will have a low removal of the pollutant. So we know that heat is influencing the volatilization, and that's the development of thermal disruption. When chemicals are not volatile enough, we are able to remove pollutant more than C40, even if they are not in the legal target. But we know that it's applicable at the extreme to heavy TORs or heavy pH. So the panel of the target is broader, it's faster. We are going on field for several months. We may apply it in situ with direct the burner inside the soil or in pile. This is a big thermopile we made in the south of France. And the efficiency, you just stop the heat when you overwhelm 95 or 99%, depending of your objectives. I told about the diversity of application. You may apply gas, electricity, fuel, depending of what you have on site. But the opposite is the disadvantage is expensive because of the cost of energy, and in the last 2 years is worse than ever. And energy consumption as a cost, and also environmental cost because of greenhouse gas emission. And at the end, you have a completely dead soil cooked during months at more than 200 degrees, for example. So there's no life in this, no carbon more, and it's only a mineral part of the soil, and it's long to re-implement some life or something that allows just seeds to germinate. Well, I made some tests, and it's quite long. I told you about soil washing. This is a picture from a lab test. In one step, you have this sand, very clayey, with evitors from a lagoon, and you turn it to a clean sand, and you have the oily part is floating on the beaker. This is the type of machine we are using. This is the first one we had before. The first point is when you create such a sand, it's a valuable material. You may reuse it in the next building or sell it. Sometimes it's possible. There are different effects, and by chance, all the effects are concentrating the pollutant in the same clay, fine powder, and also solubilization. If you have some metals, for example, you may precipitate them at the end. So the sludge contains the different types of pollution. So it's a convergence between oily and metallic pollution. But it's limited by the clay content. If you have more than 20 or 30% of clay, you don't want to apply this technique because you don't make profits. It could work, but the quantity of waste is too big regarding the amount of the starting polluted soil. It's relatively slow. This unit is nominative 60 tons per hour, but better to run 20 to 30 tons per hour. So if you have to several thousand tons, you will stay for a very long time on this site to treat. And because of the long times and energy, the need of people working on this plant, it could be expensive. And it produces also some concentrated extract that you have to destroy or put to a landfill, and it could participate to the price. I told you about the possibility of chemical action direct in situ by mixing some reagents into the soil. So there are different type of machine. Those machines are not coming from the remediation work. They are coming from the geotechniques. So they are suitable for different type of soil. We are just derivating their use, normally made for construction. So there are different vertical auger, horizontal mixer, a lot of types depending of the soil matrix. And just we modify we say to the subcontractor company, don't inject cement or lime, just take an oxidizer or a strong reductor, depending of the pollutant you want to target, and that's the way we are just playing this technique. But when you have several components in your soil, you can't mix several reagents. You can't mix, for example, an oxidant and a reductant at the same time, so it could be hard. The long-term efficiency is hard to demonstrate because you have not direct access. You have only indirect survey of what happens, so the chemical reactions that happen in the soil. You have to check them from far, and it's not always easy. Depending on the weather, too dry is not good, too wet is not good. So, and also the type of soil. If you have big boulders in the soil or building, you can't access under the building with this technique. So the number of cases where it's suitable is not so often. Finally, biodegradation, you may implement that in biopiles. Some are very rough, some are very technical, depending of the country where you apply it. It's relatively cheap. You just put them in a pile, create this reactor, and let the microorganisms work. It's not your engineers that are destroying the pollutant. It's reputed to have a low environmental footprint, and it respects biodiversity. Sometimes it enhances the biodiversity because in renewing, restoring the soil. But there are some cons also that could spend for a very long time. There are some works we are just starting for 6 months, and every 6 months we are receiving or ending one of the pile, and the total of the works is 2 years. So in some case, you don't have the time to spend 2 years on site. Some people need to work on this place or to live on this place, so you have to liberate the zone. It's also sensitive to weather. We know that when we are starting in the summer, sometimes the degradation is lowering during the winter, and it's now today it's not efficient or not cost effective to heat a biopile. The bioavailability of the pollutant seems to be the strongest limit. You have the same molecule, soil appears to be about the same, but one is removable and not the other one because of the interaction of this pollutant with some part of the organic matrix of the soil. And it's very hard to anticipate it before you go on the field to apply this. So we have different advantages or disadvantages. If I compare the biodegradation and the thermal disruption, that is reputed the strongest way to remove TPH from the soil. And what we want is that mycoremediation hope to be all the good tick, whatever the lines, and some of the points are already demonstrated, and some of them have to be demonstrated during the Life MySOIL project, and that's why I leave the floor to the next presenters.
Thank you, Laurent, of this for this overview of practical approach on remediation. And now, for me, it's a pleasure to invite Professor Alessandro D'Annibale, my colleagues, and coordinator of UniTus team in MySOIL project.
Thank you. Okay. Good morning to everybody. This short speech is expected to provide valuable arguments related to the suitability of saprotrophic filamentous fungi in bioremediation. A brief foreground before going straight to the point. The susceptibility of persisting organic pollutants to the biodegradation is obviously dependent on their degree of exposure to appropriate microbial biocatalysts. However, in heterogeneous systems such as soil, this is hindered by the propensity of these compounds to escape the aqueous microhabitats of degrading organisms, and this occurs through a variety of mechanisms, which include chemical precipitation, sorption onto abiotic surfaces, partitioning onto organic matter, and finally, entrapment within micro and meso soil pores. This obviously leads to a decline in their bioavailability and to the occurrence of local accumulation phenomena. And such accumulation frequently occurs in adverse environments characterized by the lack of appropriate nutrients, electron acceptors, and moisture conditions able supporting the contaminant degrading ability of these organisms. Thus, an ideal biodegradation system should be able of performing a thorough exploration of the contaminated environment, reaching even sorbed and pore entrapped contaminants. Moreover, its catabolic capacity would not depend on the availability of contaminants as gross substrates, but would be maintained by other compounds or by trophic supply by plant residues. It would also to be active under a wide range of conditions, being able to perform a long-range transport of water, nutrients, electron acceptors, and even catabolic microorganisms to contaminated spots. Well, saprotrophic filamentous fungi satisfy most of these requirements, and thus, in the last decades, the potential of these organisms for bioremediation purposes have been increasingly recognized. And the reasons why fungi can be excellent candidates in bioremediation is due to several peculiarities that these organisms exhibit. First of all, their exploratory growth mode, which has a variety of repercussions, which will be analyzed shortly. Then, their independence from using contaminants as gross substrates. So, although several fungi are able to exploit contaminants as energy sources, in the majority of cases, contaminant degradation has a co-metabolic character. Another point calls into question the low specificity of some of their contaminant degrading enzymes. And this is very functional to the removal of mixtures of structurally related contaminants. Although this is not a unique prerogative of fungi, they are able to produce contaminant mobilizing agents, and they are also able to perform the accumulation or hyperaccumulation of metals and metalloids, and this is useful in mixed contaminated scenarios such as military, refinery, and landfill waste sites. Last but not least, several contaminant degrading species are edible species, and thus they satisfy the generally regarded as safe requirement. And furthermore, their production composts represent an affordable and ready-to-use inoculant. Filamentous fungi typically exhibit a multicellular growth mode characterized by the presence of tubular, elongated, and branch structures called hyphae. These hyphae tend to form a network of interconnected and intertwined filaments that collectively make up the mycelium. And the mycelium network organization enables these organisms to perform an effective colonization of soil and to penetrate inside soil aggregates. The apical growth mode and the turgor pressure developed at the Eiffel tip enable these organisms to reach regions which are inaccessible to bacteria and to penetrate inside aggregates. Fungal life have an extensive surface area, and their biomass in soils generally range from 50 micrograms to 1 milligram per gram of dry soil. And in addition, several fungal species are able to develop thread-like structures made up of parallel hyphae, able to grow through vast distances across adverse environments, allowing for the colonization of areas which are located very far from the original mycelial source. Not to be forgotten is the fact that, unlike bacteria, the dispersal of the mycelia does not require the presence of continuous water phases. In addition to their apical growth mode, filamentous fungi acquire an additional chance to come into intimate contact with contaminants from the secretion of low-molecular, cysteine-rich amphiphilic proteins called hydrophobins. These proteins tend to form amphipathic layers at the interfaces, thus affect the wettability of surfaces and mediating both adhesion and surface modification. The fungal ability of modulating surface hydrophobicity exerts a positive impact on their capacity to adhere onto hydrophobic surfaces, hosting hydrophobic contaminants. The mycelial network represents also an excellent dispersion tool for bacteria. In particular, this network can act as a highway through which motile bacteria rapidly translocate, or as a subway in which bacteria just adhere to the hyphae, being passively displaced. According to the highway mechanism, the water film on the hyphal surface offers the chance to contaminant-degrading bacteria to rapidly move, whereas the movement of bacteria in unsaturated environments, such as the vadose, is limited by the availability of continuous water pathways. A further mechanism involves the ability of the mycelial networks to act as pipelines through which contaminants are uptaken and then transferred via lipid-rich vesicles with the cytoplasmatic streaming. Whatever the mechanism, the mycelial networks give the chance to increase the frequency of contact between contaminant-degrading bacteria and lipophilic contaminants, thus mitigating problems related to the low bioavailability of these contaminants and to the heterogeneous distribution of contaminants in soil. Fungal life, moreover, and their expression products, such as extracellular polymeric substances, along with plant roots, can promote the formation of stable soil aggregates, enhancing soil structure and porosity. This can lead to improved aeration, water infiltration, which can in turn support the activities of other microorganisms involved in the bioremediation process. In addition, fungi produce a set of bioactive compounds, among which, and relating to biodegradation, to bioremediation, surfactants and fungal enzymes are particularly relevant. Surfactants are reportedly amphiphilic compounds able to perform the mobilization and pseudo-solubilization of lipophilic contaminants. This table, so this biosurfactant producing capacity is rather widespread among fungi, and in particular among hydrocarbonoclastic species. And this table shows how the structural variability characterizes the production of these kind of compounds. We can find monoacyl glycerols, oligopeptide, threose and sulfurous lipids, polymeric complexes. So their surface tension reducing ability and critical micelle concentration values valuably compete with surfactants of bacterial origin, such as surfactant from Bacillus subtilis or rhamnolipids from Pseudomonas aeruginosa. Okay, and now to the enzymes. Several ascomycetes and above all basidiomycetes belonging to the ecological group of white-rot fungi possess an efficient lignin-degrading arsenal, which is in part responsible for their contaminant-degrading capacity. These fungi do not recover energy from the degradation of lignin, but through its degradation, they acquire a better accessibility to cellulose and hemicellulose microfibrils. The link between lignin decay and bioremediation potential of this organism is represented by the high degree of structural similarity which between lignin subcomponents and several aromatic contaminants. This lignin-degrading machinery exhibits several peculiar properties. First of all, a low substrate specificity. This means that they are able to perform the oxidation of a wide array of contaminants. Secondly, they are secretion products, and this means that their action is performed in the extracellular environment. And this means that contaminant uptake is not a rate-limiting factor in biodegradation. The reaction mechanism either rely on radical mechanisms or on the production of highly diffusible oxidants which can reach non-bioavailable target contaminants. And some enzymatic components of this arsenal is such as, for example, lactase, allobase dehydrogenase, and quinone reductase are able to produce Fenton's ingredients, thus producing hydroxyl radicals. This table shows a list of the main components of the lignin-degrading system of these fungi, which mostly include multi-copper oxidases and heme peroxidases. These enzymes share the action mechanisms based generally on the monoelectronic oxidation of aromatic contaminants and also on their ability to extend their substrate range by using electronic mediators, such as, for example, aryloxy radicals or dimethoxybenzyl cation radicals in the case of lactase and lignin peroxidase, respectively. Also, manganese peroxidase, which brings about the oxidation of bivalent manganese producing manganic chelates, which act as monoelectronic oxidants, is able to extend its substrate range via the use of co-oxidants, such as, for instance, thiolate anions and hydroperoxyl radicals. More interestingly, there is a group of heme thiolate peroxidases called unspecific peroxygenases, which are able to perform the hydrogen-dependent terminal or subterminal hydroxylation of alkanes. So there is also a component of this lignin degrading system which is able to act on aliphatic compounds. Okay, thank you, Sherman. In addition to extracellular enzyme systems, fungi also exploit cell wall bound and intracellular catabolic enzymes, among which cytochrome P, so mixed function cytochrome P415 monoxygenase is one of the main components in the initial phases of attack. This enzyme is able to perform the epoxidation and hydroxylation of numerous contaminants, with relevant examples being polycyclic aromatic hydrocarbons and dioxins. In addition to, there are several cytochrome P450 monoxygenase encoding genes in fungal species, and this warrants a huge variability with regard their catabolic capacity. Okay, I have to, of course, although some fungi are able to exploit organic contaminants as energy sources, their attack on these contaminants can occur extracellularly or intracellularly. Metabolites or intermediates generated during extracellular oxidation can be further converted intracellularly, or otherwise can interact with organic soil constituents through oxidative coupling reactions, giving rise to the so-called bound residues. Metabolites derived from intracellular initial attack can be excreted as such and thus processed according to the extracellular pathway, or otherwise they can also interact with the organic constituents, giving rise to the formation of bound residues. But some products can be also conjugated, giving rise to methyl, xylosyl, sulfate, and glutathione derivatives, and being excreted and being generally environmentally persistent. Or otherwise, they can be further catabolized, as it occurs, for example, for aliphatic compounds, but also for polychlorobiphenyls, thus leading to their mineralization. Going rapidly to conclusions, because my time is over. Although fungi can be excellent degraders of persistent organic contaminants, there are still few experiences at the field scale. And most of these experiences have been focused on wood preservation sites and military sites, thus targeted to the degradation of creosote, which is a mixture of polycyclic aromatic hydrocarbons and chlorophenols, and to nitro-substituted explosive, such as trinitrotoluene or trinitrotriazines. And some of these studies have highlighted the failure of this treatment to reach cleanup levels within a reasonable treatment time, or the lack of significant differences with the non-inoculated controls. And in this study, however, the fate of the inoculum and its interaction with the indigenous microbiota have been often neglected or even ignored. However, the outcome of a mycoremediation intervention strongly depends on the interaction of the applied inoculated species with the autochthonous microbiota. Thus being able to, for example, to averting the formation of dead-end metabolites. But we can be optimistic, since the advance and ensuing diffusion of high-throughput approaches, mainly relying on omics techniques, are expected to provide an increased critical body of knowledge able to support technical choices related to the setup on effective mycoremediation treatment. Thank you for your attention.
Thank you, Alessandro, for your detailed presentation. And now is the moment of last presentation for this session. It's a pleasure for me to introduce Tatiana Stella from M3R company. The floor is yours.
So thank you, Silvia, for the introduction. Yes, I'm Tatiana Stella. It's working. Can you hear me? Okay. I'm Tatiana Stella from M3R. I'm the executive director, and M3R is a company based here in Milano, and that is working with AnyRewind in many projects dealing with bioremediation, phytoremediation, and of course, mycoremediation. But I want to say that I'm coming from the group of Maurizio Petruccioli, Alessandro Dannibale, sorry, it's emotional for me, and Silvia, so it's really nice to meet you here again. And I'm going to present something about the upscaling and degradation efficiency of total petroleum hydrocarbons contaminated soil treatment at full scale. So we are speaking about another scale, not anymore laboratory or pilot. As you know, TPH are maybe, or maybe yes, the most spread contaminants in the environment, and especially in contaminated soil. And of course, how we can treat them. We can apply in situ technology, if it's possible. It's of course, the best choice, because it means that we don't need to excavate the contaminated matrix. However, most of the time it's not possible. So we are applying ex situ technology. So we need to excavate the soil. And when we speak about bioremediation, ex situ technologies, of course, we have to mention biopile, which is a technology that exploits the ability of microorganisms, fungi, bacteria, to degrade organic pollutants under aerobic conditions. And we can choose, we can choose between two different technologies. We have the dynamic technology and the static one. In the first case, the oxygenation of the contaminated matrix is due to a periodic mechanical turning of the contaminated matrix. On the other side, when we apply static biopile, the oxygenation of the pile is due to a fixed aeration system. So these are the two technologies that we can use for the treatment of TPH contaminated soil. But when we have to face with this technology at industrial scale, of course, we have to think about so many parameters, okay? That I want just to summarize in these three categories. The first one, the chemical and physical properties of hydrocarbons, because of course we have different classes of hydrocarbons with different volatility, toxicity, solubility, and you will see later there is a point, the weathering of the contamination. And then of course we are speaking about bio-based technologies, so we have to assess the microbial community properties and metabolic capabilities. And of course, we have to assess all the environmental conditions that can impact on the growth and the activity of the microbial community. For example, temperature, pH, but also the content of nutrients, electron donors, and acceptors. So these are all the parameters that we have to assess before designing an efficient treatment at full scale. Going to chemical and physical properties, as I mentioned before, the weathering. What is the weathering? Naturally, several physical, chemical, biological processes can occur, okay, without any kind of intervention. And what is the result? The result is a modified hydrocarbon mixtures. And as you can see here, I just prepared two profiles. The first one, contamination, because it's rich in alkane, that is the category, I would say, of hydrocarbons that are easily biodegradable. So this is a fresh contamination that we can somehow easily degrade by biological techniques. But in this case, you see, there are not alkanes anymore. it means that is a whole contamination where the light fraction, the more volatile, are already removed from the mixture, so it's more recalcitrant to any kind of biological treatment. So the assessment of the weathering that is possible by fingerprint analysis is a priority before designing a bioremediation approach. And then microbial community. As I said, we are speaking about bio-based techniques. And we use biomolecular analysis, DNA-based techniques, because these techniques allowed us to see how many and which kind of microorganism we have already in the contaminated matrix. So we applied both qualitative analysis, next generation sequencing, so we can see which kind of microorganisms there, but we can also perform quantitative analysis of target genes. It means genes that are directly involved in the biodegradation process. So we can combine these techniques and to gather a lot of information about the microbiological status of the contaminated matrix. And as I said before, we have to assess all the environmental conditions that can impact on the microbial growth and activity, and how we can optimize. We can use, for example, biosurfactants or chemical surfactants because we can increase the bioavailability of contaminants and so helping, let's say, microorganisms to degrade them. We can use nutrients because, of course, microorganisms need nutrients. But sometimes we don't have proper microorganisms in the contaminated matrix, so we have to add some specific microbial inocula. But of course, we can use amendments. When I'm speaking about amendments, I'm speaking about green compost. You will see spent mushroom compost. They are, I would say, waste or secondary products, but it's not correct, because in terms of circular economy, is an added value substrate that we can use in bioremediation. And it's really cheap. And this is important when we are working, of course, at industrial scale, because the cost of the treatment is reduced. But to practice, these amendments are rich in nutrients, in microbial biomass, and they can act also as bulking agent. And here, the last part of my presentation, I selected some pictures about some project that we were working on during the last 4 years related to biopile treatment of TPH contaminated soil in different treatment plants here in Italy, in both static and dynamic configuration, okay? And I just selected some pictures you see in the first one. There is a biopile where we use green compost, for example, as amendment. In the second one, the spent mushroom compost, that is the topic of this day. And another case, we use also an oxidant, but we use the oxidant as pre-treatment because in that case, we had a really hot weather contamination. So it was not easy to degrade only with bacteria or fungi. We need to modify somehow the hydrocarbon mixture to make the mixture more biodegradable. And then, of course, we apply nutrients or some microbial inoculum, and here just a picture from last month in a treatment plant where we set up several biopiles. And of course, in all these application cases, we control all the conditions, so the oxygenation, as I said, humidity and temperature. These are really important. However, we will say that once we designed the bioremediation of a TPH contaminated soil in a biopile plant, we have to define also a monitoring plan, because the monitoring plan is necessary to modify several parameters when the process is ongoing, okay? So to make the process more effective, more efficient. So we need, of course, to check the concentration of TPH, chemical analysis, but it's not enough. We have to check several parameters such as temperature and humidity, because we are speaking about bio-based technology and microorganisms are related to that. We can perform respirometric tests, so we can assess the amount of oxygen, because of course we are speaking about aerobic processes. So if we see that there is a consumption of oxygen, it means that the process is going on. And consequently also CO2, because it's formed if the process is going. And of course also methane or sulfuric acids that are produced under anoxic conditions. So if we find these compounds, something is not going well, because it means there is not oxygen for microorganisms. And of course, we also apply a biomolecular monitoring to see which kind of microorganism is there, the structure and the dynamics over time. So how it's changing, okay, during the process. And of course, we perform also ecotoxicological analysis. These are important because it's to prove that any kind of toxic metabolites is produced during the biodegradation process. And this is something that authorities often requires. And just to conclude, I select one of these projects. It's a project in collaboration with the University of Milano Bicocca, Eni Company, Eni Rewind, and HPC Italia, that is a consulting company here in Milano. Is a project dealing with the treatment of TPH contaminated soil in these agricultural areas that is close to Milano, close to Cisliano. The project was dealing not only with biopile, but also phytoremediation. There is a full-scale phytoremediation field there. But of course, we are speaking about biopile. We selected the dynamic biopile as technology. We set up 2 biopiles. The first one, we didn't have any nutrients, any microbial inoculum, it was just oxygenated. In the second one, we had some green compost as amendment. We monitored, as I said before, several parameters: temperature, humidity. About temperature, we saw, for example, that where we had the green compost, the temperature increased. It means that the process, the biodegradation process, started immediately and was going on. Here, the ecotoxicological analysis, we use the germination test. It means that if we have an increase in the germination index, there is a reduction in the toxicity of the matrix. And what we observed, it was an increase of the germination index. It means no toxicity, or anyway, no toxic metabolites were formed. But going to the chemical analysis, I want to underline, if you see here, the red one is the biopile where green compost was added. The process was much, much faster than in the other biopile, especially at the beginning. But after 2 months, more or less, the process started to slow down. But this is normal, this is typical, because it means that the light fraction, the more biodegradable, was removed. And only the more recalcitrant still remained in the matrix. So what we did, we say, okay, let's try to overcome the limit of bacteria. And why not? Let's use fungi. And we use the spent mushroom compost of white rot fungus Pleurotus striatus. That is a waste of food industry, really rich in nutrients, in enzyme, cheap as substrate, and so also environmentally sustainable. Why we use white rot fungi? Alessandro said everything before. I want just to underline, really, these kind of fungi are characterized by excellent, I would say, metabolic traits with regard to the biodegradation of not only TPH, but the most persistent organic pollutants. So complex mixture of hydrocarbons. Because of these extracellular oxidative enzymes, because they high fall growth, so they can penetrate easily into the contaminated matrix. And of course, they can tolerate high concentration of organic, but also metals, and they also are involved in soil humidification processes. So many reasons why we can use this substrate for bioremediation. But as you can see, even if we had this substrate, the rate of degradation didn't significantly increase. And this is probably due to the fact that we were using a dynamic biopile. And probably later, the colleagues from MySOIL project, they will explain that. But since we are speaking about fungi with this high fall growth, the mechanical turning of the matrix can somehow impact, okay? So it's not probably the best configuration, the dynamic biopile, for the treatment, for the application of this kind of substrate. Anyway, you see, at the end of the test, we obtained the 90% of removal of the initial concentration. And even if, okay, we had a really low level, our goal was 50 milligrams kilograms, so because we were in an agricultural areas. But then we were going on with this test, and of course I don't have time to show you, but using some surfactants, we reached 70 milligrams per kilograms. During the process, of course, we also performed some biomolecular analysis. And here I just reported the sequencing of 2 target genes. So we studied both bacterial and fungal community, okay? I want just to underline concerning the fungal community. You see, when we had the substrate, the spent mushroom compost, Pleurotus was more than 90% of the total fungal community. However, if we look at this bar, the last one, at the end of the process, Pleurotus was only 2%. And this is the main problem, as Alessandro said before, the persistence of the inoculum because of the competition with the autochthonous fungi and other microorganisms. And of course, we also quantified some target genes. We quantified the total number of bacteria, and we quantified a biomarker that is used for the aerobic biodegradation of aliphatic hydrocarbons. And also in this case, we observe an increase in the copy of number of these genes just at the beginning of the process. And then it starts to reduce, as you can see, in the last part of the treatment when the biodegradation process starts to slow down. So to conclude, I'm on time. This is my message, I will say. I want just to underline this is a message that I report in here for biopile treatment, but it's general for bioremediation. These are 3 points, really important. If you want to apply any kind of bioremediation strategy that is effective, efficient, and that you can reach the remediation goal within a time frame that is reasonable. The first one is the characterization of the contaminating matrix. We need more than the chemical analysis. We don't need just the concentration of TPH. We have to know which kind of contamination we have there. Is old, is fresh, which kind of hydrocarbons are there. And of course, we are applying bioremediation technologies. So we have to know which kind of microorganisms are already there. They are proper microorganisms, they are able to degrade hydrocarbons, we need to add hydrocarbons. So a comprehensive characterization is pivotal, I will say, for any kind of bioremediation strategy. And then, of course, based on that, you can optimize all the environmental conditions, you can start your treatment, and the monitoring, as I said before, it's really important because you can modify some of these parameters also when the process is ongoing. Okay, and in this way, as I said before, you can achieve your bioremediation goal within a time frame that is reasonable and also reducing the cost of the treatment. Thank you.
Just a few words to conclude. I want to thank you all the 4 speakers. They touch very, very different topics, but in a very nice overview. So now I guess that we learn a lot and we can understand perfectly what will be said in the next session about the MySOIL project. Do you have to say something, or I can just announce the buffet, the coffee break? So now this is the time of the coffee break.